Here's a problem that engineers and also people in other disciplines encounter, and is related to fault trees and probabilities for failures in complex systems. What follows is a fairly long discussion, so here's a brief of what we will do here. We have a relatively complex, safety-critical system, consisting of electronic and mechanical parts. Currently, the system has a given estimated probability of failure per hour of operation. Imagine that at some point there is a need to upgrade the system's reliability by reducing its probability of failure. Engineers who are faced with this task will try to use their best judgment to modify the system, until hopefully, the calculated probability of failure can be reduced to the desired level. This is often a difficult job, especially if the system has hundreds or even thousands of components. In this video we will show how genetic algorithms, GAs, can generate solutions and modify in a single run the system's architecture, at least with respect to component redundancy, to meet the new safety levels. Before we dive into fault trees, and explain how genetic algorithms can modify them, we need to explain how the two most common building blocks of fault tree work. Viewers who are familiar with logic gates and fault tree analysis may want to skip this section and move directly to our specific example, some 5 minutes further on in this video. Let's start with the top gate. Assume there are 3 inputs, A, B, and C, and an output D. The way this logic gate operates is as follows: if A is true, and B is true, and C is true, then D is true. Translated into the language of safety, for D to fail, it is enough that one of the 3, A, B, or C, will fail. But if all 3 are still going, D keeps on going. The propositional logic operator here is multiplication, D equals A, times B, times C. Clearly, it is enough that 1 off 3 is 0 for D to be 0. Applying this to probabilities, if the inputs on the left are the respective probabilities of events A, B, and C, then the probability of D is their multiplication. The second type of gate operates differently. Here it is enough that one of the inputs is true or non-zero, for D to be true. So if we talk failures again, even if 2 of the 3 have failed but the third is still going, D will not fail. The propositional logic operator here is summation, D equals A, plus B, plus C. Clearly, for D to be 0, all 3 must be 0 as well. Let's assume that probability of failure per hour is 30%, admittedly an almost unrealistically high number, but used here just to show how the math works. And this is the result. Note that 0.027 is an order of magnitude smaller than 0.3. In other words, we created triple redundancy. Going through the second type of gate, however, has the opposite effect. Here is the result, a probability of 90% that the system will fail. Using this methodology, we can build models of very complex systems and be able to estimate their overall probability of failure. If the system is properly constructed, with the right architecture and sufficient redundancy throughout, its overall probability of failure will be considerably smaller than that of its building blocks. Let's move on now to a concrete example. What we see on the left is a section from a fairly large fault tree, of a proposed design for a vertical takeoff and landing, VTOL air vehicle. On the right is a smaller section separated from the main tree. This section addresses a critical aspect of the vehicle's safety, which will be explained in a minute. The air vehicle on the left gains its lift from 2 ducted lift fans, one in a duct in front of the passenger cabin, and one behind the cabin. The control of the vehicle is obtained via 4 cascades of vanes, installed on each of the 4 ducts openings, one layer at the top of the forward duct, one at the top of the aft duct, and a similar pair below the vehicle, at the exit of the airflow from the ducts. For redundancy purposes, each cascade is divided in half, each half powered by a separate actuator, a separate processor, and a separate LVDT, short for linear variable differential transformer, to measure the movement of the vanes and provide feedback to the processor. So, in a similar manner to the scheme we saw earlier when we discussed the 2 types of gates, this time, 3 logic AND gates are connected at the fault tree on the right via a logic OR gate, because all are needed for the system to work. And at the entrance to each gate at the bottom of the tree, is one processor plus another one, so 2, in case one of them fails, and similarly 2 actuators and 2 LVDTs. So the components at the bottom have what's called double redundancy. We can see, in orange color, that while the probability of failure of the components themselves is between 1 in 1,000 to 1 in 10,000, the probability of failure of the full cascade of vanes is approximately 1 in 26,000. The other 3 cascades are identical to this one, so this scheme is repeated for them as well. This is how the full vane control system section looks for the complete vehicle. Due to symmetry, we can continue our discussion with just one of the 4 cascades, and factor in the other 3 in the probability equations. All of the blocks in the diagram represent to the vane control system itself, except 2. The first odd block represents a bird ingestion into one of the lift rotors, destroying the vane cascades on both the top and bottom of that rotor. This block is added to the tree using a logic OR gate. The second odd block is an emergency parachute that is deployed when everything else fails and lowers the vehicle safely to the ground. It is connected through a logic AND gate, because a final, catastrophic failure will occur only if there's both a total loss of control, and in addition, the parachute has failed to deploy. The calculated probability of that comes out as 1 in 27 billion per flight hour, or 2.7 e-10 in scientific notation. All of that sounds complicated, but is in itself quite simple math. There are special programs that perform fault tree analysis once we have constructed the tree itself, representing our system correctly. Modeling the full system into a tree diagram is of course a tedious task. However, much more so is the effort of putting together the system in the first place, be it a ship, a satellite or an aircraft. This effort is performed by system engineers, and is more of an art than a science. Considerable work, based on experience, intuition, and a lot of trial and error, is necessary to come up with a system that not only works well, but also meets a predetermined probability of failure per hour of operation. That's where genetic algorithms enter the picture. Imagine that we already have a design, and it already has its fault tree, and an FTA has been performed. Then, a customer approaches the company developing this vehicle, telling them that they would like to place a large order, but only if the probability of failure due to loss of control is further reduced from the current 1 in 27 billion per flight hour to 1 in 100 billion per flight hour, or 1 e-11 in scientific notation. Now, there are 2 ways to approach this. One is to look at the whole system again and design the whole vehicle differently. This option is considered out of scope at this stage in the program. The second option, which is the one we will employ, is to stay with the current design, and look at ways to increase the redundancy at the component level. Of course, we still want to do it wisely, so that any change that we make will comply with basic engineering constraints that are part of the design itself. This is a perfect task for a genetic algorithm. We just have to define for the algorithm what is technically tolerable and what is not. Let's first write down the probability expressions for every level in our fault tree. We start at the bottom row, with the given probability of failure of processors, actuators, and LVDTs. From there, we move up, combining probabilities as explained at the beginning of this video, depending on the type of gate we are moving through. Note that the equations are in general form. So the levels of redundancy, NP, NA, and NL, are now variables for the genetic algorithm to redefine, in order to meet the new goal for the system's safety level. So now's the time to start with the definition of the chromosome for this problem. We are choosing once again the convenient binary format, reflecting choices for the level of redundancy for each of the 3 component types: processors, actuators and LVDTs. To explain what we see, let's look for example at the level of redundancy of processors, NP1, NP2, NP3, and NP4. These 4 choices would look like 0100 if the genetic algorithm decides to stay with NP2, which we currently have, for double redundancy, and 0001 if the genetic algorithm decides to pick NP4, meaning quadruple redundancy for processors. Similarly for the number of chutes, NC, number of actuators, NA, and number of LVDTs, NL, where the letters U and L are added where there's a difference between the upper and lower control vanes. For example, NLU2 is a gene that represents double redundancy of LVDTs in the upper vein cascades. As in most genetic algorithms cases, the total number of combinations, even in our small tree here, is already 22 factorial, which is huge. So again, a tall order for humans. Fortunately, we have genetic algorithms to do this job efficiently for us, and in a fully explainable fashion, with the system engineers in the loop at all times. These last two are extremely important. Our fitness function is simply the probability, and we will try to get a smaller and smaller number until we hit our goal. Notice that we could have decided that cost is our fitness function, and that 1 to the power minus 11 is a constraint. But we'd like to have full visibility to the progression of the probability p from one generation to the next, so we are staying with the probability of loss of the aircraft due to loss of control as our fitness function. We will of course still include the cost of each proposed solution in the run's printed output. As for the constraints, they are in this table, together with basic component reliability and cost data. Here are initial results from the first run. We are not entirely happy with the results, because all of them show a safety higher than what we asked for. Not that it's a bad thing in itself, but it comes with a price. Firstly, the cost, but also in the need to mount more equipment, add wiring and other provisions which also affect the basic weight of the vehicle. But here's an interesting feature of genetic algorithms. Because both the crossover and mutation operators employ random parameters. Randomness affects not only individuals in each generation, but also makes each run a little different from the previous run. So the general rule in genetic algorithms is, if you're not happy with the results, run the program a few more times, with each round providing you with essentially a new set of solutions. So we did just that, and on the right we can see the results from 4 additional runs. One of those is especially attractive for 3 reasons. First, it is one of the closest solutions so far to our safety requirement with 2.16 e to the minus 13. Second, the cost is the lowest compared to all of the other alternatives, and third, this solution still stays with 1 parachute, where most other solutions are based on 2. This is important for the engineers, because the parachute is very heavy and takes up a lot of space on the vehicle. We will still continue with additional runs to try and improve that solution even further. If you recall that there are 22 factorial separate combinations to this problem, there's no risk of running out of new alternatives. However, looking again at the solution shown at the bottom, achieved after only 4 runs, it is really not a bad combination of parameters. Not an exact fit with our probability target, but still, safer than the minimum we were looking for, and a major upgrade of our system.